Hi everyone, this is Lesson 7, Video 1, Modes of Heat Transfer. Lesson 7 is dedicated to modes of heat transfer, that is conduction, convection and radiation. You learned about these in Year 9 initially and we just described them. Year 11 doesn't take it too much further than that, but we do talk about the factors that influence the rate of heat flow in conduction and convection and radiation, Year 7, and that's probably what this video is mostly dedicated to. In modes of heat transfer for Year 11, you really do want to be able to use the particle theory of matter to describe the rate of heat flow for conduction and convection. And for a Year 11 discussion of radiation, we want to talk about the factors that influence the rate of flow of heat by radiation, focusing mostly upon radiation by emissivity. By the end of Lesson 7, we want to be talking about heat flow in terms of conduction, convection and radiation. We want to be able to explain conduction and convection thoroughly using the kinetic theory of matter. We want to be able to identify and describe the factors that influence conduction and convection, as well as identify and describe the factors that influence the speed of conduction and convection. We call that rate of heat flow or power. We want to be able to identify and describe the factors that influence radiation and the speed of radiation, and we'll be focusing mostly upon emissivity for that. Looking at conduction and convection. In any system where two objects come into thermal contact with each other, heat will flow if they're at a different temperature. The thermal energy will always go in the same direction, from the hotter material to the cooler material. There are three modes of heat flow: conduction, convection and radiation. Focusing upon conduction. Conduction is most prevalent in solids. It involves the heat energy transferring through a substance. The substance itself is the conduit of the energy transfer. It is the means of the heat flow. So if the substance is not there, the conduction does not happen. In this graphic, we see the classic metal bar with a heat source applied to one end of it. We need in Year 11 to be able to describe conduction in terms of the particle theory of matter. In this graphic, we see the Bunsen burner supplying heat to one end of the rod. And we remind ourselves that in solids, which is where conduction mostly occurs, particles are fixed in their location about the solid, vibrating. The degree of their vibration is an indication of how much kinetic energy they have. If we supply energy to one end of a metal bar like we see here, then the particles will become more agitated at that location. Their increased agitation disturbs the particles nearby them, and that is then passed along the rod. The energy is passed along the rod in the form of agitation of particles. In the sector entry for this lesson, I've included simulations which allow you to see this illustrated on the screen in front of you. I encourage you to look at them and see if you can describe in words what you're seeing in images. In Year 9, we talked about conductors and we talked about insulators. In Year 11, we still talk about conductors and insulators, but we think of insulators as poor conductors. Everything conducts heat eventually. When we think of poor conductors, or we also call them insulators, they can conduct in the absolute absence of any other chemical in the region. They will conduct eventually, but what will happen first is that they will go through chemical reactions. So before the heat can flow through the material, energy boundaries which allow chemical reactions to occur will be achieved first, and then the material either break down or combust. That's why we think of them as poor conductors or insulators. In Year 9, we talked about good conductors being metals, and we left it at that. In Year 11, we say that good conductors rely upon that particle theory of conduction that we spoke of previously, but they also take advantage of their delocalized electrons, which are not fixed in location. The electrons move freely about the material, distributing heat energy to a much broader section of the substance, and examples of these include aluminium and copper. So that pretty much covers the Year 9 content for conduction and convection. In Year 11, we take it up a notch because we consider the factors affecting the thermal conduction. The first factor affecting thermal conduction is the temperature difference across the material, the temperature gradient. The thickness that is being used to pass the energy through, the thickness of the material. A metal rod will conduct heat through it. A thick metal rod will conduct heat faster. The surface area exposure to the heat source and the surface area exposure to the heat destination is going to influence the rate of heat flow through the material. And then there is the nature of the interparticle bonding within the material. This is an intrinsic property, a physical property of the material itself, which is unique to each different conductor. This equation that we see here is not one of our Year 11 equations. It doesn't feature in your formula and data sheet, but it sums up factors affecting thermal conduction. You should know these letters by now. Capital Q is heat, lowercase t is time, A is surface area, delta T is the temperature gradient, L is the length of the material. K is a physical property or a constant that is used in this equation to represent conductivity of the material, an intrinsic property of the material. This equation shows us that Q over T That's rate of heat flow, how fast the heat flows. Q over T is proportional to the temperature gradient. Delta T is another expression for delta T is temperature gradient. What's the temperature at the entry point of the material? What's the temperature at the exit point of the material? The larger the difference between those two temperatures, the larger the temperature gradient. L is the length of the material. This is inversely proportional to the rate of heat flow. So the longer your conduit for passing heat through, the slower that rate of heat flow will be. Surface area in contact with the heat source, surface area in contact with the heat destination. This is proportional to the rate of heat flow. Here's a visual representation of the factors influencing rate of heat flow through conduction. Delta T, again, the difference between the temperature at the heat source versus the temperature at the heat destination. Large delta T equals greater heat flow or rate of heat flow. Length of the material, the longer your heat conduit, the longer your substance that you're conducting through, the slower the rate of heat flow. Surface area exposure to the heat source and surface area exposure to the heat destination. The greater this is, or the greater these are, the greater the rate of heat flow. Very often in Year 9 when we talk about conduction, we talk about heat flow through a metal rod. This graphic is a cross-sectional image of a piece of piping. So if you can imagine hot water passing through a pipe, you'll soon notice that the pipe becomes hot to the touch from the outside. Well, of course, conduction is happening from the inner region of the pipe, where the hot water is located. And in those situations, it's good to imagine what are the surface area, delta T and L values for the equation in this situation as well. So of course the delta T is the temperature difference between the heat source inside the pipe, it could be hot water, and the heat source outside the pipe. The length of the conductor is the thickness of the pipe. The surface area exposure to the heat source is the surface area inside the pipe in contact with the hot water. Now let's turn our attention to convection. Whereas conduction was the predominant form of heat transfer in solids, convection is the predominant form of heat transfer in fluids. And in Year 11 physics, when we talk about fluids, we are talking about both liquids and gases. Fluids will expand when heated, but the expansion of fluids need not be uniform. And when we say fluids expand, if we try to explain that in terms of the particle theory of matter, what we are saying is that the fluid is made up of particles, and the spaces between the particles on average dictates the volume of the fluid. So when we say fluids expand, the spaces between the particles become greater. The nature of the space between the particles and the expansion of the space between the particles need not be uniform when a fluid is heated. Regions within the fluid which are closer to the heat source will experience an increase in the kinetic energy of the particles near to the heat source much faster than those particles further away from the heat source. And so those particles near to the heat source are going to become much faster, they're going to become much more agitated, and the spaces between them will be forced to increase much faster than the particles in those regions of the material which are further away from the heat source. If the average space of the particles in the regions of the material near to the heat source is greater, due to the increased kinetic energy of the particles in the region near to the heat source, if that space is greater, then that region is going to be less dense than regions of the material which are further away from the heat source. Being less dense, and also due to the fact that the fluid is not fixed in its shape and the particles are free to move about each other, being less dense, that region of the material which has received the heat will be forced to rise by denser, cooler regions of the material where the spaces between the particles are smaller. Implied within this statement is the assumption that the material exists within a gravity field. You won't see convection occurring in the International Space Station where there is apparent weightlessness. In Year 12, we'll talk about what apparent weightlessness is. To sum up convection, the consequence of convection is that if you supply heat to the lower region of the material, the heat will flow very quickly to the top region of the material, and the material will, as a general system, will rise in temperature from the top and move its way down. This, of course, raises the question, hang on a second, why do lakes freeze from the top when the top of a fluid is warmer than the bottom of a fluid that's undergoing convection? And if you remind me in class, we'll discuss that one. The equation that you see here is a sum of the factors that influence the rate of convection. This equation Q on T equals HA delta T helps to describe the rate of heat flow from a hot object to a fluid. Again, the symbol should be pretty familiar to us. Q on T is rate of heat flow, that's heat per unit time, lowercase t is time. Capital A is the surface area exposure to the heat source. Delta T is the heat gradient between the heat source and the fluid at large. And H is a coefficient specific to the fluid in question. That's the end of the video. What now? Take a moment to jot down the ideas from this video in your physics notebook. Try to do it from memory. Don't go back and just copy things out. Read and take notes on Chapter 2.2 and 2.3 of the Pearson Physics 11 text. Complete Chapter 2.2 and 2.3 questions from the Pearson Physics textbook. And when you're ready, have a look at Lesson 7, Video 2, which will be focusing on radiation. And that'll bring us to the end of modes of heat transfer, conduction, convection, and radiation. And will also be the last video in our thermal physics part of the course. I hope this was useful.